I want to wrap up today's class by talking about some of the applications of spin. So the first one I want to talk about is to give you a little bit of a sense of where that fine structure in the hydrogen spectrum comes from. Remember at the beginning of the class how I said that H-alpha spectral line ends up getting split into a pair of lines? Well, it turns out to have a lot to do with the electron's spin. So let me give you a sort of a very hand-wavy plausibility argument that sort of suggests where this might come from. Okay. So to be hand-wavy, because we're being hand-wavy, I'm going to just go back to the Bohr model for a second, even though it's wrong. So in the Bohr model, right, we know that we have our proton and we have our orbiting electron. It turns out that to analyze what's going on, it's helpful to think about this from the rest frame of the electron. Yes, this is weird, we are going to a non-inertial reference frame, but bear with me, and there's a way to do this carefully beyond the scope of this class. So if you're in the electron's rest frame, it's sort of like being on the Earth and what people thought for centuries and before Galileo, right? It looks, if we're sitting here on the Earth, it's really tempting to think of the Earth as fixed and then the sun orbiting us. Similarly, in the electron rest frame, the electron sort of sees itself at the center, and the electron sees the proton orbiting it. So here's how here's what the spin has to do with it. So if I have this orbiting proton, right, that orbiting proton is an electric current. And I'm going to say orbiting with a giant grain of salt, because we know that's not quite right, but for purposes of being hand-wavy, we'll just go with it. Orbiting proton creates a magnetic field because a little orbiting charge is a current, which is a magnetic dipole, which generates a magnetic field. Right? Because the electron has spin, right, therefore it has a magnetic dipole moment mu associated with that spin. And because the z component of it can be positive or negative, right? I can think of this as there's two possible directions, as it were, for this electron magnetic dipole moment vector. Where the physics comes from is the energy of a dipole in a magnetic field, or potential energy specifically of mu in. And again, you may have learned this in 118, that the potential energy, and I'll write U for the moment, for a dipole in a magnetic field depends on the dot product of the dipole moment with my magnetic field. So here's the thing, right? Depending on mu z equal being positive or negative, hopefully it's sort of at least vaguely suggestive how I can have sort of two possible signs for this potential energy due to what sort of essentially I can think of myself as aligned with the magnetic field or anti-aligned with the magnetic field produced by the proton. Right, so let me highlight this. So this is from spin, and this is from my proton. So this is what's formally called spin-orbit coupling. If you take an advanced quantum mechanics course, you may learn how to calculate with this and handle this in the correct quantum mechanical formalism using something called perturbation theory. It turns out you actually have to account for relativity when you do this as well, so it's really, really awesome. You should take more quantum. But hopefully this at least lets you sort of see how sort of having two possible spin states could possibly give rise to sort of a splitting of the energy level for n equals 3, which ultimately gives rise to the splitting of that H alpha line you can see in the hydrogen spectrum. Another application of spin that I'm only going to have time to mention very briefly is something relevant to both chemistry and physics. It turns out that because electrons have spin 1/2, they are what are called fermions. So so there's something called the Pauli exclusion principle you might have learned about in chemistry. And what the Pauli exclusion principle says that when you have fermions, right, so no two fermions can be in the same quantum state. Now, we won't have time to talk about multi-electron atoms, but this turns out to be really critical for thinking about the electronic structure in a multi-electron atom. If you think about something like helium, which for neutral helium has 2 electrons, to lowest order approximation, we can ignore the interaction between the 2 electrons. And then roughly the electron energy eigenstates are very similar to the energy eigenstates we saw for hydrogen, right? So if I were to sort of imagine putting 2 electrons in, let's say, the ground state of helium, so it's just like what we had before, where for hydrogen, where there's a 1s or a n equals 1, L equals 0 state. It turns out that those 2 electrons have to have opposite spins. So if I were to denote the state with arrows, it turns out that in the ground state you have 1 electron with n equals 1, L equals 0. Because L is 0, we have m equals 0, but ms equals 1/2. And then this one has m equals 1, L equals 0, and then ms equals minus 1/2. So it's the Pauli exclusion principle that requires my electrons to have a different quantum state because they have the sets of quantum numbers in their entirety are different. And ultimately, this is sort of what leads to the electronic structure of atoms, and it's it's the reason atoms and solids behave the way they do. And also the fermionic nature of electrons has lots of other implications in things like particle physics. So lots more to explore here if you go on and learn more about quantum mechanics. Another connection to more physics is that it turns out electrons aren't the only particles with spin, and specifically spin 1/2. So protons also have spin, and it turns out that the spin of protons has applications in things like nuclear magnetic resonance. So if you're a chemist, you may have used NMR to elucidate the structure of organic molecules, or maybe you've had a medical MRI scan. MRI stands for magnetic resonance imaging. So because protons have spin, they have a magnetic dipole moment because of their spin, And they respond to magnetic fields. And looking at the response to magnetic fields is the physical basis for NMR and MRI as an imaging technique based on measuring this kind of nuclear magnetic resonance. So I think if you take 421, you will have worked out the sort of the formalism you need, which is really just based on time evolution with the Hamiltonian, the same way we talked about in this class, to analyze what goes on in an NMR experiment. The last application that I want to close with is just to give you a flavor of something we call quantum computing, which is actually a very hot area of physics research right now. So you all studied, I think, basic digital electronics in Physics 120. So you'll remember that when we talk about like binary logic in Phys 120, right? So computers work because there's only two binary logic levels. Everything is either a 1 or a 0. The idea of quantum computing is to do something like this, perhaps with spin. So instead of having, say, a 1, maybe the analog for that, so it's a quantum bit or a qubit, you could have a quantum bit that it could be either spin up, so you could have this sort of chi plus spinner, or spin down. And this would, correspond to 1 or 0. But the thing that quantum bits or qubits can do that classical bits cannot is that a quantum bit can be in a superposition state. You can have a qubit that looks something like 1 over root 2 chi plus 1 over root 2 chi minus. So qubits can be in superposition states, unlike classical bits that really only can be 1 or 0. We don't have time to go into this in more detail, but it turns out that there are some algorithms that are hypothetically a lot faster with a quantum computer that's able to work with bits like this than they would be on a classical computer. So one of them is this algorithm for factoring large numbers that is the basis for a lot of the encryption that we have on the internet. So like when you go in and like log into your bank account, or frankly probably all the student records, like if you go into Homework Connect, I'm pretty sure that hopefully is all encrypted. So a lot of that encryption is based on it's really hard to factor large numbers. But if you have a quantum computer, you could, in principle, factor large numbers and like defeat, this sort of security. So as by one of the professors I had for graduate quantum mechanics in grad school was saying, if you can solve quantum computing, you could, in principle, go and rob banks from all over the world, where they'll probably catch you for doing it. So don't try that. But let me just go to my computer now to show you one slide of one way in which we might be able to implement, or actually we are already starting to implement quantum bits using spin. One last thing I wanted to show you here as something that's actually a very hot area of current research. It turns out that if you have a diamond lattice, so diamond is carbon, and carbon sort of likes to form these tetrahedral bonds, you can have what are called defects in a diamond crystal. There's one particular defect called a nitrogen vacancy center, or an NV center. So in this kind of defect, instead of a carbon, you have a nitrogen atom substituted in, and then you have that plus a vacancy or a missing atom. Now the physics here is well beyond the scope of what I can tell you, but it turns out that this defect ends up having effectively a spin, just like we've been talking about spin for electrons and other particles. And so there's a lot of interest right now in controlling, measuring, and manipulating the spin states of these NV centers for applications like quantum computing. One reason it turns out these NV centers are useful is that they turn out to be fluorescent. And so you can actually see them under a microscope if you stick a sample of diamond under the microscope and shine some green light on them. And that's a picture that you've got here. And this is from Lily Childress's group at McGill, where they're investigating some really cool physics with diamond NV centers. So today we've had a sort of a whirlwind tour of spin and like how to describe it and some of the things you can do with it. So hopefully this leaves you like raring to go for more quantum mechanics. So take 421. What we'll do for recitation on Thursday is I'll start a little bit the discussion of nuclear, and we'll continue that discussion to wrap up on Friday. See you then.